Kia ora and welcome back. Now that we've discovered what normal subgroups are, we can use these to build groups out of other groups, and these special groups are called factor groups. So the idea is, if we take the cosets of a normal subgroup, these cosets actually form a group themselves. And it turns out the fact that these normal subgroups are normal is really important for these cosets to actually form a group. Otherwise, they just form a partition of our group, but they don't themselves have a group structure to them. So we're going to first define what this means, and then we're going to explore a little bit about how we can use these things. So let's dive straight in. So our theorem here is that the set of all left cosets of a group, of all left cosets of a normal subgroup of a group, is a group where the operation on the group is multiplication of coset representatives. So the theorem here says that this set is actually a group, and the name of this group is the factor group of G by H, or sometimes called the quotient group of G by H. So if you ever see people dividing groups like this here, that's what we're talking about. We're talking about the quotient group or the factor group of G by a normal subgroup H. Alright, so before we can actually make use of this, we'd better prove the thing. Okay, so we've got a little bit of work here to do because some of this is not so clear-cut as it initially looks. So first off, we need to actually make sure that our operation is well defined. And what do I mean by well defined? Well, think about it. We're defining an operation by which we combine two sets as an operation on their coset representatives. So I've got sets AH and BH here, and I'm combining them to give me ABH. Okay, so if I take these two sets, AH times BH, what if I had, I know that if I take a different coset representative A prime, that's true, and BH equals B prime H. It doesn't matter which of the elements I choose from the coset to be the representative, I still get the coset. So what if ABH was not A prime B prime H? Okay, so let's say if I accidentally chose different coset representatives that gave me a product of these things that didn't give me the same coset, then this operation that I've specified here would make no sense whatsoever. Alright, so what we have to do is we have to verify that actually it doesn't matter which choice of coset representative we have, that our operation is going to give us the same resulting coset no matter what. So we need to show our operation is well defined, i.e. that our mapping from our quotient group, or two of them, that's our AH and our BH, into our quotient group is a function. Okay, so we're going to choose A prime, B, and B prime, such that AH equals A prime H and BH equals B prime H. Okay, then, we know that if AH is equal to A prime H, we also know that A prime is equal to A times H1. They only differ by some factor in our subgroup H. And B prime, likewise, is going to be B H2 for some H1 and H2 from our subgroup. Then, now what we're going to make sure is that we're essentially going to show that these two things have to be exactly the same coset. So then A prime B prime H is equal to A H1 B H2 H. We know that H2H is just H, so that equals A H1 B H. Now is where we have to use the fact that H is normal, which means that equals A, H1, HB. Okay, remember, if you've got a normal subgroup, left and right cosets are the same thing. So I can switch around BH and turn it into an HB. And then that H is going to swallow up the H1, so that equals A, HB. And now, again, I'm going to use the normality of it to put the H back on the other side of the B again. It's going to be equal to ABH. Okay, hence, our operation is well defined and doesn't depend on the choice of coset representative. That's good. So it actually makes sense to talk about this thing. It did require us to use the fact that H was a normal subgroup for this to actually work, but we know that we can see now that the operation does work. Okay, so now that our operation actually makes sense, we can now go ahead and do our usual thing to prove this is actually a group. So we need an identity. Well, we can see hopefully fairly clearly that AH is just going to be equal to EH, which in turn is just going to be equal to AH. So EH, which is just H, is the identity. Okay, so the subgroup itself is the identity of our quotient group, or our factor group. Inverses. Again, I'm going to do a little bit informally. A inverse H times AH. Remember again, our operation to combine cosets is just to multiply the representatives. That just equals EH equals H. So A inverse H is the inverse of AH. Okay, it's all working very nicely. And finally, associativity. Again, this one comes quite straightforwardly. AH/BH times CH is equal to ABH times CH equals ABCH. Now we can use the associativity of the group G itself. It's going to be A times BCH, and then we can expand it out again, which will be AH times BCH, which will equal AH times BH times CH. All right, that's good. So now we've established that actually, so long as our group is normal, and we did use that in our proof of making sure our operation was well defined, so long as our group is normal, then we can form a new group by just considering the cosets as a group themselves under the operation where we combine cosets by multiplying their coset representatives or coset leaders. Okay, so now seems like a good time to jump into an example and just to see how this works in practice. Okay, so let's take the quotient group of the integers with 4z, which is just the subgroup generated by 4. Okay, so let's just remember how this works. So recall that z is abelian. And remember that all subgroups of abelian groups are automatically normal. So that means 4z is going to be a normal subgroup. So hence 4z, which equals, just as a reminder, 0 plus or minus 4 plus or minus 8, etc., is a normal subgroup. Of z. Okay, so what are our group elements? So remember, the group elements are just the cosets. So we're going to take the different cosets of this subgroup. So 0 plus 4z is just simply going to be the subgroup itself. This is our identity. And that's going to be, let's write it out ordered this time, -8, -4, 0, 4, 8, etc. Now we're going to choose an element that's not in our subgroup and use that to build our next coset, which will be 1 plus 4z, which is just 1 plus 4z, and that's going to equal, let's line it up, -7, -3, 1, 7, 9, etc. So adding 1 onto everything there. Another coset will be 2 plus 4z, -6, -2, 2, 6, 10, etc. You can see how this works. So this is we're taking cosets of an infinite group, but you notice that these are the various cosets. 3 plus 4z. We don't have 3 yet, so we can make that into a new coset. -5, -1, 3, 7. I've done something weird here. That should be a 5 in that earlier one. There we go, fixed it. 7 and 11. And if I go to 4 plus 4z, I'll get back to where I started. There are no others. So remember, just practicing our terminology, we say that 4z is an index 4 subgroup of z, because there are 4 distinct left cosets. Even though our group is infinite, we still only have finitely many cosets of it. Alright, so let's see what this group looks like. So we'll make a Cayley table and see how they combine. So we'll have 0 plus 4z, we'll have 1 plus 4z, we'll have 2 plus 4z, just not overwrite it, and 3 plus 4z, and then down the other side we'll have the same thing, 0 plus 4z, 1 plus 4z, 2 plus 4z, and 3 plus 4z. And you can see that because we're just adding together the representatives, we're pretty much just going to get the same thing, 1 plus 4z, this will be 2 plus 4z, this will be 3 plus 4z, 1 plus, 2 plus, I'm just going to skip right in the 4z's just to save space. We're basically just doing the table of Z4 here. You can see we're just adding modulo 4. That will be 4z itself. That will be 3. That will be 4z itself. That will be 1 plus z. That will be 4z here. That will be 1 plus, and that will be 2 plus z. 2 plus 4z, sorry. Okay, so you can see that this Cayley table here looks very much like the Cayley table of Z4. We just got the extra plus 4z's on every entry, but otherwise it's the same thing. So clearly, and you can do it formally as an exercise if you want to, the factor group of Z, of 4z and z, is going to be isomorphic to Z4. And generally, this is true for Zn as well. Okay, we can repeat the same exercise for any n greater than 0, and you'll get that Z quotient nz is isomorphic to Zn for n greater than 0. Okay, so there's an example. So we can see that all of our Zn groups are isomorphic to a quotient group of a subgroup of the integers with the integers. Right, for our next example, we're going to go back to S3, and remember in our previous video, we showed that the alternating group A3 is a normal subgroup of S3, and the cyclic subgroup generated by one of the transpositions, e.g. 1, 2, is not a normal subgroup of S3. So we're going to illustrate how this works, because what we should find is that the quotient group should, try that again, S3 mod A3 is going to be a factor group, whereas it won't be a factor group with respect to 1, 2. So we can actually observe this property in the Cayley table of the group itself if we color code the cosets different colors. So I'm going to draw the Cayley table of S3, and I'm going to have elements of A3 are going to be black, and my other coset, which will be 1, 2 times A3. I'll write those elements down in green. So remember, these are the elements 1, 2, 1, 3, and 2, 3. So if I now build the Cayley table of S3, and I'm going to order them so I've got the A3 elements first, epsilon, 1, 2, 3, 1, 3, 2. And then, like I said, I'll write down the coset elements in green, 1, 2, 1, 3, and 2, 3. Let's make that a little bit bigger. Same thing down here, epsilon, 1, 2, 3, 1, 3, 2. And 1, 2, 1, 3, 2, 3. Now what I'm going to do is I'm going to fill out the Cayley table, and I'm going to just write down the element in the correct color depending on which coset it comes from. We'll see what happens. And a miracle has occurred, and here we go. If we were to squint our eyes here, we kind of see that we've got a black blob in the top left, we've got a green blob in the top right, a green blob in the bottom left, and a black blob in the bottom right. So what we can kind of see here is we can see the structure of the quotient group according to those colors there. So if we were to squint, then what we're basically seeing is this Cayley table here, A3, and here's our coset, 1, 2, A3. So now if I draw the Cayley table of the quotient group, then essentially I'm seeing this pattern reflected in my bigger Cayley table here. So A3 here, A3 here, and then I get 1, 2, A3 here, and 1, 2, A3 here. So this part is my coset, 1, 2, A3, as is the top right, and then the top left and the bottom right are just A3. So you can see that these are the same kind of picture, and the second one is like a representation of the first one if I squint my eyes so that I can't see the details, but I can still see the colors. Okay, that's all very well, but what happens if we do this with a subgroup that's not a normal subgroup? So I'm going to use my cyclic subgroup generated by 1, 2 now, this one up here, and I'll see what happens if I perform the same exercise. So let's just make some more space and give that a go. So first off, what I'm going to do is I'm going to form my 3 cosets that partition my group S3 into pieces. So here they are. So I've got 1, 2, the cyclic subgroup generated by 1, 2 itself. That's my first coset. My second one is going to be 1, 3 times that, which is going to be my green one. And my third one is going to be my blue one. And that's going to be 2, 3 times that cyclic group. Now let's do the same exercise as before and build that Cayley table. Okay, so let's just start filling this in. I've ordered my elements so they're sorted by their cosets and written down in their respective colors. So if I go down across completing this Cayley table now, and again I'm going to have those there, then this is just the epsilon row, so it's all going to work nicely. 1, 3, 2, and 2, 3. Now we do the 1, 2 row, so we're going to get 1, 2 here. Epsilon. So far so good. We've got our red block in the top left, like we'd hope to see. But then when we move across to our next one, we're going to get 2, 3 when we multiply 1, 2 and 1, 2, 3. And 2, 3 is blue. So you can see our color coding has gone out the window here. And this one is 1, 3, 2. And then if I keep going across there, I'm going to get 1, 3 and 1, 2, 3. So you can see that if I do not have a normal subgroup, my Cayley table does not split itself up nicely into blocks of solid color, and we don't get this sort of subgroup structure. This is because these 3 are not a group. Because our cyclic subgroup is not a normal subgroup. Okay, now I won't bother filling in the rest of the table because we can see what we need to see straight away, but we don't get this nice block patterning as we'd hope because we don't actually have a factor group here. All right, we're going to do one more example and to show that we have no subgroup of a certain size in A4. All right, this is a cute little one. This is a way of showing that A4 has no subgroup of order 6. Okay, so the way we're going to go about this is we're going to assume that it does. So suppose A4 has a subgroup of order 6. Okay, now we need to note something first. Note that the size of A4 is equal to the size of S4 divided by 2, which is 24 divided by 2, which is 12. So this subgroup would be index 2 because it's half the size of the group, and hence, let's give the subgroup a name, shall we? Let's subgroup H will be index 2, and hence H would have to be a normal subgroup of A4 because all index 2 subgroups are normal regardless. Then, since a quotient group, which will be A4 divided by my subgroup H of index 6, has order 2, and orders of elements divide orders of group, of groups, the two cosets in this quotient group must both be order 1 or 2. For all alpha in A4, coset squared, no matter what alpha is, whether it gives us the H coset or whether it gives us the other one, the square of that thing has got to be equal to H. Which implies alpha squared is in H. Okay, but if you look up a Cayley table for A4, what you'll see is that alpha 4 actually has 9 different squares. So just open up, find a back of galleon or something, Cayley table for A4, you'll see there are 9 different things down the diagonal. So it has 9 elements of the form alpha squared, and the order of our subgroup is equal to 6, so we have a contradiction. We can't have 9 different things in a group of size 6, so we have a contradiction. And A4 has no subgroup of order 6. Not 6 factorial, just 6. Okay, so that's a cute little example of how we can apply some of this theory. The trick with the index 2 subgroups being normal is a good one to remember. And now we've sort of got our heads a little bit around the idea that once we have a normal subgroup, we can build it into a quotient group that tells us something about the group itself. That's enough for this video. So next video we're going to do a few sort of miscellaneous theorems relating to this before we move on to our next topic. So we'll see you then. Ka kite anō.